Hi there, and welcome to Mr. Carlson's lab. In this episode, we're going to design the lower digital circuit board for this frequency counter build. That circuit board will also have the power supply on it. After we're done with the build, we'll fit it into that little bakelite box, and we'll do some testing to see how this little thing performs. There'll be a whole bunch of little things in between as well. So let's get started. Before I start designing the lower circuit board for this Nixie project, I'll fill you in on some of the things that are running through my head as I'm putting this whole thing together. And one of the biggest issues that I'm going to be dealing with is size issues. I have to fit these transformers here and everything you see on this breadboard into that little bakelite Numicron clock case, as well as fit that display with that circuit board in there as well. So for those of you that are tuning in right now, this is the Numicron clock case. Pretty neat looking little bakelite box. And I figure that this would look extremely neat sitting on top of some old receiver, giving it a digital display, or even any old communications receiver. Just a very neat looking bakelite box. Now, oddly enough, this chunk of bakelite is what inspired this entire project. It's amazing what a piece of bakelite can do. So it's flawless. The case is absolutely flawless. This is just tape residue, and I haven't cleaned it up yet. I'm just using this for, mocking the thing up, really, is all I'm using this for. In the end, I'll clean it up and put a polish on it. It'll look really, really nice. So, again, I got to fit all of this stuff inside that case. So, right away, I know there's no way I can make this thing through-hole. This is all through-hole components here on the breadboard. I'm going to have to turn this thing into a surface mount project, much like the little display board there. I need to fit these power transformers inside there as well. So what I've done is I've set these power transformers beside this little display board, one here, and I've set the box over the top, and I think I'll be able to fit all of that in there. There is some space to the sides. Now, as well as doing that, I also need to fit in these capacitors. These are through-hole components and some 1N4007s, and this is a voltage doubler circuit here, and I'll get into showing you the schematic and exactly how this is all working here in just a little bit. So lots of stuff that needs to fit inside there. So, lots of basically mocking things up and trying to center things. And of course, as I'm doing this, I want to minimize this circuit as much as I can. So what I've done is, in order to get rid of this entire crystal oscillator section, in my boxes, I found a bag full of fixed 4 megahertz crystal oscillators. So that'll reduce some size here a little bit. And I've, tried a bunch of them out, and I've used the ones that are, I've pretty much, I guess you could say, I've graded the components and marked their exact frequency on them. So this one here is very good. Works very, very well. In fact, they're all very close. So, nothing that I really need to worry about, especially for a 5-digit frequency counter, right? So this will reduce some size here, and I've also perfected the front end. So I've made the front end a little bit more sensitive, and I'll go over that on the schematic and show you exactly how I've done that, and I've also eliminated some components in that as well. So that's the whole idea of this is, I want to minimize this as much as possible because, again, I'm pretty much running out of space inside that box. This is going to be a pretty tight little fit. I'm beginning to plan that lower circuit board, and these are some of the thoughts that are running through my head in this planning stage. So one of the things that I need to deal with is that I already have that upper display board built, and somehow I need to fit that onto that lower circuit board that I'm going to be designing now and have it centered so that the Nixie tubes are right in the center of the window. Another thing I'm thinking about is how I'm going to fit those little transformers in there, how hot are they going to get, and I'm dealing with the size restrictions of that little bakelite box. Now, one very important thing that I'm planning right now is I'd like to be able to use this thing as a regular frequency counter, and of course, because this is going to be a digital dial, it needs to be programmable so I can use this with all sorts of different receivers. And what is the best way to go about doing that? So I'm digging through my stuff, and I found this little box of switches here, and I've got these neat little rocker switches and all sorts of switches that I could use to program this thing with, and then I find these little rotary binary coded decimal switches, and these are definitely the answer. They're small, and if I point the little arrow to 0, that turns this entire frequency counter into just a regular counter. And the minute that I rotate this thing off of 0 here, I'm now affecting the way that the counter works, and basically I'm programming it with some form of an offset at that point. So that gives me the ability to basically lift the cover of the box, the little bakelite box, off and get a screwdriver in there and program all of these things to a set IF of some sort. So say I wanted to program this frequency counter to 455 kilohertz, I can adjust all these little rotary BCD switches accordingly, and it'll do that. And just say down the road I wanted to use this thing with a signal generator or something. That means I need to return this to a regular frequency counter. I can lift that little bakelite case off and return these all to 0. Now, that little bakelite case is in such nice condition, I don't want to harm it in any way, shape, or form. I don't want to put a switch on it. I don't want to drill holes in it. I don't want to do anything to that case. So in order for me to change the offsets here for a different receiver, I will have to remove the little case. I'm not even going to put a switch in the thing to turn the thing on and off. What I'll do is I'll probably put one of those little roller switches in the line cord, and I'll just use that. Again, that little bakelite case is in such good condition, I don't want to, tamper with it in any way, shape, or form, so that it just looks completely stock, no drilled holes or anything like that. So I figure this is the way to go, and I have quite a selection of these things. I have them on an angle as well, and I'll probably end up using those, and I can just adjust these from the front, because that other circuit board is going to have to be elevated, and it'll have to sit above these somehow. So I'm thinking that, of course, if these are straight up, it's going to be that other circuit board is going to be in the way. It'll be covering them. So I have ones in this little box here that are on an angle. I'll probably end up using some of those, and that should make the programming pretty easy. So that's the next step. I have to figure out how to place all this stuff on the circuit board and, of course, get all the measurements made. I have to fit that circuit board into the bottom of the bakelite box and align up the original mounting holes so that I can mount this to the the original little, they have standoffs in that box. They're kind of extruded bakelite standoffs, and they just hold the bottom portion of the original clock in. So I want to be able to mount the factory circuit or the circuit board now to those factory mounts. I don't want to add anything, and again, I don't want to drill the box at all. So I have to do quite a bit of measuring. So I'll get started with that, and we'll take a look at this thing on the computer here next, and I'll show you exactly my thought process as I'm putting this whole thing together. I'm starting the build of the lower circuit board right now and starting to lay components and things like that. So this is my thought process as I'm putting this whole thing together. First of all, the bottom board complexity is a little bit more in depth than normal, just because I've already built that upper display board and I kind of have to plan around that. And I'm glad when I put that upper display board together that I left a lot of room on either side. This is much larger than it is originally. I've just made it bigger so I can work on it a little easier. This is the original size of that upper circuit board layout, and this is all surface mount components I'm building on this right now. So back to the explanation here. So what I've done is I've just basically copied that upper circuit board and I cut out everything on the inside and I just left the alignment markers. So I can take that upper circuit board right now and put it on top of this, and those standoffs that are going to extend the upper display board will align up perfectly with these dots. So that gets one big hurdle right out of the way. I have these alignment markers here so I know exactly where the upper board will end. And of course, when I start working on the lower board's dimensions and everything, I already know the size and how to place this, and I can center this in the middle so that I can align this up so that the Nixies display correctly in the center of that little bubble display window there. So in order to align up these little rotary BCD switches, these are the little pads for the rotary BCD switches right here. So there will be 6 of them and they'll fit right here. So before I cut out that upper layout, I took 6 of these pad layouts and placed them directly below each of the Nixies. So basically I added these onto the schematic where the Nixies were before I cut everything out, and that places these little rotary BCD switches directly below the Nixie tubes so that this rotary BCD switch will affect the Nixie that's directly above it, and so on and so forth as I'm moving along. These here are just supply rails, so positive and negative. And these little 0402 parts are the 10k ohm resistors that tie to ground. So you can see that this here is the ground rail and that this is the positive rail. These here are those 74HC 192s and they're surface mount packages. So these are all those ICs right here. These are the 74HC 574s that are right here. And those are those they act as memory in this circuit. They're classified as flip-flops. So I'm working my way around, and I imagine that when I put this thing together, I'll probably move this out of the way. This was the stock location for the blank, the 5 volts, the B plus, and the ground. So I'll probably just get rid of this, and I'll have to move that somewhere else. I'm thinking that I'm going to mount the like an edge connector kind of idea at the edge of the circuit board here, and I'll probably just fasten the wires to the rear of the circuit board at this point. So this is where I am right now. Now I haven't measured up the lower circuit board yet to fit it inside of that bakelite box, so I'm going to have to measure that all up and make another pad layout so that that will mount to the existing standoffs inside of that brown bakelite box. And then I'll have to center this and make sure that this is far enough away, because there's kind of a step inside of that brown bakelite box, and I don't want this to, I don't want the little rotary BCD switches to hit the bakelite at all, and everything has to be perfectly centered. And so again, that does add a little bit to the complexity, but in the next step here, I'll explain exactly how I go about doing that. The circuit board layout is pretty much complete at this point. I may do some, fine tuning. I might move my name around or something like that, but the layout has been double checked and triple checked, and I'm pretty sure it's going to work at this point. So pretty much ready to etch the circuit board. Just print this off and go at that particular portion of the project. So I'll explain exactly what I've done here. So when you're looking at the different colors here, the black that you see is on the back side of the circuit board, and the green is on the top side of the circuit board, and these kind of are reddishy brown looking colored kind of dots are on both sides of the circuit board, as well as these little alignment markers here. This is classified as board level here. So that's how this works, and we're looking through the top side of the circuit board through the bottom side of the circuit board right now. So if we were to hold the circuit board up to light, this is how it would look if we had enough light behind it. So when you get to this kind of a complexity in a build on a circuit board, it helps to eliminate one layer and work on one layer, and then put the top on, and then of course you have to connect some vias and go back and forth between some layers, and it helps for sizing. So basically what I do here is I'll go here into layers and just get rid of the top layer and just work on the bottom layer like this. So on the bottom layer here is the RF input section here and the RF ground, and then over here I've got the DC section and the DC ground. The RF ground and the DC ground are tied together at the capacitor here, and that just splits off into the board here. And when you're designing something like this, it's very important to understand the differences between RF grounds and DC grounds, and that's a pretty in-depth explanation. I really won't get into that in this video right here, but in the future I will start explaining the differences and the thought process behind that. So when you're designing something like this, again, in this sort of complexity, you want to make sure that there's absolutely no issues after the design's done. So you pretty much want to, take everything into account so you don't have to redesign the circuit board again, because that'd be a real pain, right? So that's what's going on here. There's let's see, what have we got? This is the rotary BCD switches here, and there's more rails that run up here, and then this is the connector that goes to the top board. And this is the capacitors mount here, and the 2 diodes and the voltage doubler circuit are here. This is one transformer on this side of the circuit board, and this is the main power transformer on this side of the circuit board here. These are the rectifier diodes here, a 5-volt regulator, a little bit of heat sinking. I know it's not going to need it. I left some copper on here, and when I drive the screw through this into the standoff inside of the extruded standoff inside that bakelite box, that screw would act as a sink as well. But again, this regulator just gets barely warm, so I'm pretty sure it's not going to even need that in this design. Filter capacitor, 2200 microfarad, 25 volt cap will sit up here. These are 250 volt 47 mic caps that sit here, and 2 1N407s through-hole components that mount here on the top side of the board. This is a little blanking switch that I added, so I can basically de-blank the upper board if I want, or I can leave the blanking feature on, so I figured I'd just add that in. Bypassing capacitors all over the place. I'm not taking any chances. Lots of bypassing capacitors, basically one for every IC, basically below the supply lines. Keep the design as quiet as possible. So when I was sizing the lower board, this is the layout for the lower board right now. And this is, again, this is made big. If I go, like, this is the actual size of the circuit board here. So I'll just make that big again. So What I did is I measured up the distance between the, the extruded standoffs in the bakelite box, and the distance between this particular portion of the box and the distance between the center here and this portion of the box. And this turns out to be the board edge right about here. And I'll have to basically round the corners off, or, put them on an angle, because the actual bakelite box itself, they've kind of filled the corners in a little bit, which is kind of weird. But I'll probably have to round those off, and this should just drop right in, and this should fit right on top of those extruded standoffs, and this will hold the board in place. The upper display board will mount to this right here, and it should be centered right in the window. So basically what I did is I measured the center between these two extruded standoff holes, and that gives me the center basically of the window. And then I just adjusted this entire board basically on the lower board until I had this in perfect alignment with the center, and that should put this little rotary BCD and the Nixie tube above it, this middle Nixie tube, right in the center, because there is a Nixie exactly right above every one of these little rotary BCD switches, so that should align this to the window. Now the board edge, I've eliminated the board edges. There's board edges here, 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 and here. This is the mounts for the upper board, and there's enough room to fit those little transformers in, and that worked out very well. So there should be a little bit of space between the bakelite box and that upper board. And I've also kept the the capacitors far away from the transformer. This is a little, not incredibly far, but spaced a little ways away from the power transformer. The power transformer does get a little bit warmer than the step-up transformer here for the B+, but absolutely fine. You can keep your fingers on it after 4 or 5 hours of use. It's absolutely fine. So the RF input will come to this point right here, to these pads, and run right into this section right here, little RF amplifier here. And then right above this is how it gets squared off. There's that 74 AC14 right above it, which is that Schmidt trigger, and there are a bunch of inverters, and it just basically takes this sine wave and squares it off for the input. So what I'll do is I'll toggle layers here, go to the top layer and eliminate the bottom layer here. So this is the top side of the circuit board, and all these little dots you see here are all vias. They all got to get joined to the bottom side, so I have to drill those out and put a little piece of wire in there. So this is the upper transformer. So basically we'd be looking at the top side of the board, and this is where we'd see all the ICs right now, because this is the top side. So this is mounted right above that little RF section here, and that squares the signal off, and the signal path runs down through here through a little 100 ohm resistor into the 74HCT00. That little 100 ohm resistor is there just to basically get rid of some ring. That's all that's there for. And there's also some ground plane below this to keep this shielded right up to here. So if I go back to the layers here and put the bottom layer back on, you can see the bottom layer goes through here. And if I like this and go to the top layer, so you can see the pads here. The trace runs to these little pads here, and then you can see how it runs above this little bit of shielding here, and that's just to keep that all shielded. Now this isn't trimmed to 50 ohms or anything like that, because the impedance of that particular portion of the circuit isn't going to be like that at any rate at this point. So basically it's just acting as shielding. This is going to be a square wave that's going to be changing in frequency however we feed this thing, basically up to well, the layout went to about 39, 38, something in there, megahertz, right? So in the end, we'll see how this works. I imagine this will probably go a little bit higher than that, just because the layout is optimized, and the traces are as short as possible, and there's quite a bit of RF consideration on this particular circuit board. And if you're interested in hearing my thoughts in the design of the RF section and how I put all this together, you can leave that in the comments below. If you're interested in just an explanation on how I planned this whole thing out, and how the actual in-depth thought of the RF section and placing this together, I can go through that as well. If I hear enough about that, I'll put something like that together. I'm not sure if that's something you'd want to hear or not. So anyways, the thing is ready to print off at this point. I've got blank written on here, and my name on the top. The top doesn't need to get mirrored, but the back side does. So the back side of the board, again, is not mirrored, but the printing is. The top side in its entirety has to get mirrored. So when I'm printing this off, that's how that will come out. And I'm doing the sandwich method here. Basically, it looks like a folder, and I'll show you that here in just a little bit. I'll show you exactly how I align the top and the bottom of the board, and how I put that onto the actual the piece of copper circuit board, and we'll get into that process then. The first thing I do after the circuit board is etched is drill out all the holes, and there are lots of holes to drill here just because of all the vias. And I'll focus in on those vias here in just a moment. There's vias everywhere here. So what I'll do is I'll start with those, and I'll work my way up in bit sizes here to the larger pads. Now I've got all of the leads of the components pre-measured, and I know exactly what drill bit to pop in for, the leads of the different components. So that really makes the drilling process quite a bit faster. After I've done that, you can see here I've got some alignment markers in the corners of the board here. I'll draw a pencil line through here, and I'll take this piece of board to the bandsaw and cut as close to that line as possible, and then I'll plane the rest down so I get a nice square board in the end. Now, something that's kind of odd about that Bakelite box is that a perfectly square board won't fit because they've kind of trimmed the corners, or in the box they've actually filled the corners. So what I got to do is trim the corners on an angle, and that should make this fit into the box, and I'll show you that here in just a little bit. So those are the next steps. Now, one of the most common questions I get when people see circuit boards like this is, what do you do about the plated through holes? Well, the truth of the matter is, you got to populate every single one. So what I do is I put a little piece of wire through and solder it on both sides, and that's the only way that you can do plated through holes in a board like this. So that's why in a production environment, if you were to make lots and lots and lots of these boards, you would want to export this to a PCB house. But since I'm only making, well, right now I'm only making one, but down the road if I find another Numicron case, I might make another one or whatever. At that point, doing it like this is absolutely fine. This is the very first board, and I also get to proof my design by doing it like this. So just say that, this is the RF section over here. This is where the signal comes in. Say there's some sort of an oscillation happening because of component spacing or something like that. I can perfect that here. Whereas if I was to, just design this thing and immediately export it to a PCB house, I wouldn't have that option, and I would get a whole number of boards back with possibly an issue. And there's not only that to think about, there's, component spacing. How will this thing fit into the box? Do I need to move anything around? I've done lots and lots and lots of measuring here, so I'm pretty sure I'm absolutely fine. I've measured this thing every which way. But still, there always is that chance. So doing it like this first is a really good way to do things. Another thing people ask me is, how do you match up these little pads on this side to the pads on the opposite side of the board? And what I'll do is, I'm not sure if I demonstrated that very well in one of my other videos here, so what I'll do is I'll get my projector out and I'll show you exactly how I do that. It's really quite simple and it's foolproof. It works every single time and it's perfect. So you can see here, I'll just move some of the light out of the way. You can see there's light shining through these holes, and that's because the pad on the opposite side of the board is perfectly matched up to this pad here. If they're not, you get a shadow in the hole, or the hole would be dark. But you can see every single one is absolutely fine. So I'll just zoom back out here. So you can see on this side of the board is this row here. So there's really no trick to it. It's really quite a simple process, and I'll show you that here in just a moment. This is the overhead projector that I use for aligning the two sides of my toner transfer method for my double-sided circuit boards. These old projectors can be purchased for relatively cheap. I think I picked this one up for $20 or something like that, and it's in very, very nice condition. The standard precautions apply if you're going to be doing this kind of thing. Remember that there's a very bright light underneath that Fresnel lens. You don't want to stare into it. So if you're doing this, you're doing it at your own risk. Usually what I do is I cover up the unused portion of the Fresnel lens with a piece of paper, so I don't do that. I have flashed my eyes once with this, and it isn't a pleasant feeling, let me tell you that. So just take care if you're going to be doing this method. But using something like this really makes aligning the two layers a lot easier. You could dim the light down as well inside. You don't need to have it so incredibly bright. It just depends on the paper thickness that you're using. If you're using a very thick paper, you do need the light to be quite a bit brighter in order to shine through the thick paper. I've recently changed my paper. I found a very, very good paper to use, and that really works well with the toner transfer method. That the circuit board that we're doing right now, I used this paper with, and it's made by HP. I'll find the number here. I'll put it in the Show More tab just below. So if you're using the toner transfer method and you're using a laminator like I am, this particular HP paper, boy, it works very nice. Much better than the other paper that I was using before. So the thicker the paper, the harder it is to make the toner stick. The hotter the actual unit needs to be, the hotter the laminator needs to be. So this paper is really quite thin, and the nice thing is it takes water very, very well. So when you put this thing in water, you run cold water over top of the paper and it soaks up that water in about 20 seconds. So whereas that other paper I was using, the thicker stuff, you could run water on that stuff for a half an hour and it wouldn't take. You actually needed to press the water into the paper. So I'll link that paper in just down below. I'll put a product number and stuff just below the Show More tab if you're interested in using that particular paper. Again, I've got extremely good luck with that. I think it's the best paper I've used yet. So anyways, what I'll do is I'll reposition the camera. I'll get the camera just a little bit closer to the overhead projector here, and I'll show you exactly how I do this alignment. I have pieces of paper taped to the unused portions of the Fresnel lens just to keep the light out of my eyes. And the bottom portion of the toner transfer method packet is taped to the actual Fresnel lens. And the reason I've done that in this case is just to hold it steady, just to demonstrate this. Normally I don't tape that to the lens, I just hold it with the bottom of my hand and then I'll slide this around, align it. Now I have two pieces of tape pre-cut on the corners of this overhead projector here ready to go, because once you have this aligned, you don't want to be fumbling with your hands with trying to pull a piece of tape off or anything like that. So you want to have everything ready to go, because if you move this even just a little bit, your alignment is out. So what I'll do is focus this in a little bit closer here so that you can actually see the light shine through the holes here. You can see that when I put this on top, it almost becomes transparent. So what I'll do is just zoom this in a little bit, and I'll put this on top. And then what I do is, you can see, you just put some pressure on it, and you just want to see light through all the holes. Now you can see it looks like there's light through this side here, but if you go over here you can't see the light because the alignment isn't perfect on this side. So what you need to do is align both sides. You have to make sure that you can see light through all the holes. And it's looking like that's pretty good. You can see light through all the little holes. Oh, see, it's very easy to move this. And realign this side here again. This is why you don't want to be fumbling for tape as well. So you can see these look like they're aligned and these look like they're aligned, but you can see that we can't see light through these holes, so you know that we still need to move over a little bit, and you can see how clear those got. Like that. And that's about it right there. That's as close as we're going to get. So now that I have this, you can see I'm holding this really steady. So what I'm going to do is take one of these pieces of tape and very carefully put the tape on one side like this, and then I will do the exact same on the other side. I'll just slide this over a little bit so you can see. Grab my piece of tape from this side. And there we go, and there's the packet method, and it's done, and you can see all the light through all the little holes. So now all I would do is now I would separate the packet, and then I would stick a piece of circuit board between the two just like this, and our alignment would be absolutely complete. So when we're aligning the circuit board in here, you also want to be watching this right here. So you also have the circuit board centered, and it's very easy to see because the circuit board is dark in the center here, right? So what you would do is just get the circuit board aligned and pretty much centered in the middle here, and you're ready to go. So let's see if I have just a blank piece of copper laying about here. I think I do. It's not cut to size or anything, but we'll just use this as an example. Here's a blank piece of copper. So what you would do is you would just stick this between it right now, like so, saying of course this was cut to the appropriate size, right? And once that's all done, you would just hold this steady and you would feed it through the laminator, and your layout would be perfectly aligned. You can see even though the packet is separated, you can still see light through the little circles here. It works out perfect every single time. I haven't had one time, I don't think, where it has been misaligned like this. And that's just how easy it is to align this up. The board is plated now, and I'm ready just to pre-fit this, make sure everything fits in the box here. So it has to fit down in this little lower area here. And as you can see, it fits quite nicely. I left a little bit of extra room just so I could move this around. So now the big thing is, let's see if the mounting holes line up. These are most likely going to also be the mounts for the feet on the bottom, or to hold the bottom panel, because there's going to be another panel that'll fit in here. I'm not sure. I might use sticky feet on a piece of aluminum, or I might use a piece of circuit board. I'm really undecided at this point what I'm going to do to shield the bottom here. So far so good. Looks good. Yeah, there's a little bit of room even for movement in there as well. So everything worked out quite well. I've taken the Nixie board, the board with the display, and I've put it on top of these little holes here, and it just fits right on top there, so that's okay. That's already done. So this was the last test. So that's how this fits down in here. They've kind of cut the corners on an angle in here, so I've just rounded the corners on the circuit board. And that just makes for a nice easy fit. And again, I left a little bit of room so I can, move this around in here a little bit. So everything's on track, everything's working out. Now I'm going to start putting in the little vias and start putting on some of the smaller surface mount components first, and then I'll work my way up to the larger parts. Usually what I do is, when I solder all the ICs onto the other side here, I clean the board first. I'll pretty much put in the adjustments for programming the the offset in the frequency counter here. I'll put those in last, just because I'm going to use either acetone or probably lacquer thinner to clean the board off, and I don't want to get any kind of chemicals inside those little rotary switches there, those little binary coded decimal switches. So those will be the last things to go in, and then when I want to clean the flux residue off, I'll just use a Q-tip and clean the bottom side here, and that should do that. And of course you don't want to get any kind of chemicals on the transformers or anything like that, because they do have tape on the windings, and acetone and lacquer thinner, if you're going to be using that kind of a chemical like I do, it's a little bit hard on that kind of stuff. It's hard on plastics and things like that. So as I say, I put the tender stuff in the last portion of the build, and then that way I can just clean the small areas with a Q-tip. Usually when I'm soldering all the ICs on the other side of the board, there's quite a bit of flux residue. To clean that with a Q-tip is extremely time consuming. So what I do is I usually get a small glass container and put a bit of lacquer thinner in there, and I just scrub it with a toothbrush, and in a few seconds it's you can pretty much just wipe the thing off and it's clean. Versus if you were going to use a Q-tip and clean it, you'd probably be there for 10 minutes or so. So that's really the difference. So that's the next step. I'll start putting in all these little vias and start putting on the 0402 components. They're the little 10K resistors are down here, and just work my way up in size. I'm in the process of installing the wires in the vias here. So what I'm doing is I'm just basically populating all the vias with a stripped piece of wire. So the first thing that I do is I put some screws through the board here just to elevate the board off the table surface here, and by elevating the board off the table surface, when I stick the wire through, it protrudes through the other side of the board, so I can very easily solder it. When I'm done with this process, I usually take the screws out, and I have kind of a non-stick kind of grip mat that I put this thing on, so when I'm working under the microscope here and I'm moving around, the board isn't sliding around with my hand, because that's a real problem when you're working with some really small parts like 0402 stuff. When I get to that, I'll populate a couple 0402s here, and I'll show you exactly how I do that as well. So I've got a piece of wire here that's stripped, and the wire diameter is about 0.0175 or something like that. Very close to, and the holes are drilled, the via holes are drilled to 0.018, so the wire slips through. It's a little bit snug, not too bad. By having the hole a little bit bigger, when I trim the end of the wire off here, it kind of puts a bit of a pinch on the end, so it allows me to keep populating this thing without too much grief. If you or drill the holes to the exact size of the wire, you're fiddling around and trying to push the wire through the hole. I just want to get this process done as quick as possible. So it seems to be about the right number. So about 0.018. So what I'll do is I'll just look for a via here, and I'll just poke the wire through. So right there, then what I do is just make sure that the wire is all the way through, and I trim it just above the board surface a little bit. I'll leave actually quite a bit above, and then I'll solder it on one side, do the entire one side, and then I'll flip the board over and do the other side. So you got to be kind of quick with this, though. You can't be taking a lot of time with your soldering iron, especially when you're soldering the vias on the other side, because the wire conducts heat really quite well, and it'll desolder this side of the board, and sometimes you pull your little piece of wire out of the via. You don't want to do that, so you got to be kind of quick on the other side. So that's where the magic of RA flux comes in, and it makes this job quite a bit easier. You just touch it with your iron and it's soldered, and it does a really nice job. So this is a relatively painstaking process, putting all of these things in, and you just take your time and work your way around the board and just fill them all up like so. And when you're done, you carefully inspect to make sure that you haven't missed any of the little vias. So you can see some of them are when you peen the edge of or pinch the edge of the wire there, sometimes it doesn't go through as well. And of course, aim is a big thing too. I'm not using the microscope at all right now. I'm just using my plain old eyeballs. So there we go. And pretty much that's what I'll do for all the little vias. When I'm done with all the vias and I got them all soldered, what I'll do is I'll come back and again I'll show you some 0402 soldering. I'm ready to start putting on the 0402 parts right now. So 0402 is the size, and these are the 10K resistors right here. They are pretty small. So this is still workable by eye, but I prefer to use my microscope. It's just a little bit less eye strain, especially when you're doing a whole bunch of this stuff. So the first thing I'm going to do is grab some of my RA flux and put a bit of RA flux on that pad, or the pads, and I'll grab one of these resistors here. Now you want to make sure that the tip of your iron is just wetted. So basically, just a little bit of solder that's on the tip of your iron is going to be enough to do this. So there it is. Now I like to center things up, just because that's the way I am. So that's centered up, and then when you've got the one side soldered, you just go over to the other side with a little bit of solder. This is pretty big for this job, but I usually do pretty good. There it is. No problems. And then I go back and finish off the other side, and there's one 0402 part installed. And I just continue to do that all the way along. It goes pretty quick. So the vias didn't actually take all that long. It probably looked a lot worse than it was. So that's what I'll do, is I'll finish populating the board, and I'll be back. The circuit board is now fully populated, and with all the parts on, it's a little bit easier to see what I had in mind. I've also attached all of the data wires that run up to the display board. So what I did is I took the display board and put it on top here, just like this. This is how it's going to sit when it's actually in the Bakelite box. And bent these over here and plugged them in, and then I just bent the wires over and pre-measured them up so they all have a kind of a uniform arch at the top, so that looked pretty good. This is the power connector here. So we have a yellow wire, which is a B+, which is about 175 volts or so. There's a space between, so there's no connection there. The next one over is 5 volts, which is red, black is ground, and blue is for the blanking feature, to turn the blanking feature on and off. So I'm pretty much ready at this point to apply power to this thing and see if it works. I'll fasten this down because it would be absolutely disastrous if this twisted. It's really slippery on here, and this is 5 volts and negative here, so if I can see that standoff just running on top of there. No disasters. So start placing your bets. Is the thing going to work? All I have to do is put in a line cord here in the back and give it some AC. Maybe I'll attach some wires to the input as well, and we'll see what the sensitivity levels are like as well. So I had really good sensitivity levels on the breadboard itself, and whenever you take something off a breadboard and usually put it onto a circuit board, if you have good results on the breadboard, you'll have very, very good results when it's on the circuit board. So there's shielding that I've done in here and all sorts of other things. There's quite a bit more planning in here, and I've laid things out to try and optimize the RF section. So when we have this thing all hooked together, I'll put everything together and I'll flip it upside down and I'll show you. So that's what's next. I'll put the power cord to it, and the moment of truth awaits. This is the underside of the fully populated circuit board. I've installed the line cord. This isn't the line cord that I'm going to keep on this, but this is just for test purposes, so I've just pretty much just tacked that in. This is the RF input section right here. This is the RF ground right here. So what's going to happen is the notch in the bakelite box is right about here, so that little notch where all the cords run out, right about here. So what I'm going to do is solder in a piece of really small coax to this area here. This is the RF input. This is the signal input pad right here, and this is the RF common. So I'll solder the braid here and then make a loop in the coax and then just run the coax out that little notch. And it'll be the same with the line cord. The line cord will be soldered on the bottom here and it'll run out that little notch. I'll have to figure out some form of a restraint. So this is the main power transformer right here. These are the diodes in the power supply here. So we get about 12 volts DC or something like that on this point. Goes into the 5-volt regulator here, and we get 5 volts all over the board. So this is the RF ground here, and this here is the DC ground right over here, and it carries all over the board. It's the ground and positive for all the logic ICs. The AC lines carry from this transformer secondary over to this transformer secondary, and we get a step-up effect, and there's a voltage doubler here, and that supplies the voltage for the Nixie tubes. And that's how that all works. This is a 5-volt and common line over here as well. All the lines to the data outputs, and this is the bottom side here of all those little rotary BCD switches over here. And that's really it. Not a whole lot to explain. These capacitors here are all ceramic capacitors, and these are just all bypassing capacitors everywhere. There are no bean counters, so I'm going to put them everywhere and definitely make sure that the circuit is quiet. So pretty much every IC has one of these across its supply lines or very close to it. That's the bottom side. So what I'm going to do is solder on 2 small wires here and feed this thing with some signal and see if the thing works. Here's the unit all put together and ready to test. The roll of solder you see in the back is just to hold the line cord from popping up. And I've got a little red and black lead attached right here. Nice flexible wire so I don't rip the pads off. That will attach to the signal generator. So what I'll do is I'll quickly turn it on and make sure everything is working okay. And if it is, I'll reposition the camera and we'll give it some signal. So here we go. And it's looking good so far. So I guess I could quickly test the blanking switch here. Let's just test that while we're here. Yep, it's working good. So no blanking now, and now it's blanking. So that's working well. So I'll just reposition the camera and we'll feed it some RF and see how that works. Just before I feed the front end of the frequency counter with some RF, I figured it'd be a good idea to test out these little red rotary BCD switches. So I'll turn on the frequency counter here, and I'll turn off the blanking function, and I'll just rotate these, and they should count to 9 as I'm rotating this. Looking good so far. Okay, all is good. Let's give the little frequency counter some RF and see how well it works. And while we're at it, why don't we also test out the blanking? Alright, so I've got my signal generator set to 1.455 megahertz, and the output level is set at 200 millivolts. It's not switched on right now. So what I'll do is I'll turn this on and we'll see if we get a frequency reading. And there it is, 1.455 megahertz. Now what I'm going to do is I'm going to reduce the signal level of the signal generator, and we'll see when the frequency counter drops out. Now, right now it's at 200 millivolts, and it's running through some 50 ohm cable. The output of the signal generator is also 50 ohms. The input of the counter has a 50 ohm termination, and it's also DC blocked, so this should be a very accurate measurement, aside from a little bit of exposed cable here. Now, in the end, when I have the actual cable running into this, the cable I'm going to be using with this, it'll be shielded directly into the unit, and I'll redo the measurements here, but I imagine it's going to be very, very close. So this little bit of open cable here probably mean a little bit at the higher frequencies, but nothing too much at the lower frequencies. I'm kind of nitpicking here a bit. But in the end, I'll take a whole bunch of measurements, and I'll have all those measurements here. So we'll just do this kind of as a pre-check. So I'll start turning down the output of the signal generator right now. You'll hear some clicking. That's it changing ranges. So right now we're at 100 millivolts. That's 80 millivolts right there. 70 millivolts. So right now we're at 50, right now exactly 50 millivolts right there. So this is working very, very well. So I'll keep going. And it drops off right at 48.6. So 48.7, 48.8. So 48.8 it stabilizes. So I'd comfortably say 50 millivolts down here. So I'll turn the signal generator up to 50 millivolts and we'll see if it stays working at 50 millivolts. I'll move up in megahertz increments here. So I'll adjust the frequency. I'll leave it at 0.455, so I'll go to 2.455 and 3.455 and I'll just do that. And we'll see how well it works at 50 millivolts. So here we go. Blanking works very well. So pretty much all the way up to 30 and a bit megahertz here, 30.455, it's completely stable at 50 millivolts. That's pretty good. So I'll keep going up here. You can see it's getting a little bit unstable up here. So I'll just up the output level here. So that's a 50.4 millivolts. So it needs just a little bit more. That could be due to the exposed lead here. So we're probably getting a little bit of some reflection going on. So I'll bring this up to say 60 millivolts just to be safe. So I'll bring it right up to say 60 millivolts. And I'll keep moving the frequency up. Not bad. And it's getting a little bit unstable at 41. So I'll keep going up here. And it's stabilized at 61.5 millivolts. Now I imagine we're really starting to get to the top end of the ICs here. And that's 42, and it completely goes haywire after that. Yeah, it just goes haywire. So 41.455 is the top end for the counter here. I could probably critique it a little bit. It's maybe a little bit more than 455, but I'd comfortably say 41 megahertz would be the top end of the counter. So it's working very, very well. And right now I'm at 64 millivolts. That's where I'm sitting right now. So working extremely well. The front end is nice and sensitive. So with a small buffer circuit hiding inside of the receivers that I do, this should work very, very well. One of the most important features of this little frequency counter is the fact that we can use this as a digital frequency readout for an older radio or communications receiver that we own. So for example, say you have a really neat looking old wooden radio in your house somewhere and you'd like to give it a Nixie Tube digital frequency readout. Well, this will absolutely work for that. Or say your favorite communications receiver is a Hallicrafters SX28A or SX28, or say a Hammerland HQ129X. This will absolutely work as a digital frequency readout for that communications receiver. And the reason it will is because it's programmable. And that's what these little red rotary BCD switches are for right here. Now, I go through the exact programming process in the earlier videos in this series, but for those of you that have just tuned into this video here, I'll briefly explain this again. So I'll just give you an example of a standard super heterodyne radio and how it works, all right? So say you're listening to 1000 AM, all right, or 1000 kilohertz or 1 megahertz, however you want to look at that. Say the IF section in that receiver is tuned to 455 kilohertz. The oscillator in that receiver will most likely be operating at 1.455 megahertz, just like you see on this display here. So in order for us to use this effectively with a receiver, we need to mathematically take that 455 off the display so it reads where we're listening to on the dial, not 455 above all the time. So this is why you can't use a normal frequency counter as a digital readout for an old receiver. And to tell you the truth, most communications receivers work on this same principle right here. They're basically just have a display that's doing the math. So in order to program this thing, it's a pretty easy process. All you do is you get a calculator, enter 100,000 into the calculator, take away the IF frequency, 455. Gives us 99545, and that's what we would program into this display right here, and it would mathematically remove 455 from the count. It would just read 1000 on here. All right, so again, it's 100,000, take away the frequency in kilohertz. So just for example, say you had a 1.5 megahertz IF, you would enter it as kilohertz. So it would be 100,000 take away 1500, and that would give you your result. So the easiest way to program this thing is to remove the signal input. So just basically disconnect the signal input cable from the source. In this case, I'll just shut off the signal generator, so that mimics disconnecting the signal cable. And what we want to do is we want to program this for 99545, and that will remove 455 from the count. So again, we have 1.455 megahertz right here. So after we do this, it should just read 1.000. All right, so let's program this thing. Very simple. 99545. Now I'll turn my signal generator on, and magically that 455 will be missing. There you go. It's reading the frequency that we would be listening to on the radio right now if we had a receiver with an IF of 455 kilohertz. And that's just how easy this thing is to program. So this whole counter project worked out very, very well, and I would definitely call this a success. I'm very impressed with just the signal level that this thing takes to make the thing read. It was in the between 50 and 60 millivolts of input RF. Very, very happy with the result here. So I still have to hook up the cable to this thing and do some final measurements, without this, kind of an alligator clip connection here. So we'll see if that does improve anything. I'm not really expecting it to do too much. Maybe at the higher frequencies it might improve it just a little bit. But so all in all, I'm very, very happy with the results. This is the finalized and amended schematic that I used to build that bottom digital circuit board with. So you'll notice a few changes in here. One of the changes that I've done is I've shuffled these gates around just a little bit, just because in the layout of that circuit board, this worked out a little bit better to attach to pin 5 here. So nothing's changed there, I've just shuffled them around. This is where those rotary encoders would attach to. So the common pin of those rotary encoders would attach to 5 volts, and then when you rotate those rotary encoders to 0, basically they're open, so these 10K resistors take over and it just turns this thing back into a normal frequency counter. So that was a nice little feature. I also noticed that when I was drawing the layout on the computer there, that pin 11 of this 74HC192 attached to pin 14 here. So I had to correct that. So pin 14 of all of these 74HC192s attaches together. Pin 11 of all of these 74HC192s attach together except for this one. Pin 11 of this IC just attaches to positive. Now, one other thing that adds a little bit more confusion is pin 14 of this IC attaches to pin 11 of this 74HC574. So you can see we have 11, 14, and 11 here. It would have been much nicer if they would have made this pin 14 as well. That would have really lessened confusion, but this is just the way that the ICs are built. So I've also modified the RF input section here just a little bit. It was an attempt to reduce a bunch of parts. I wanted to get rid of the VRs and a choke and things like that, but I ended up adding more parts anyways, so I think it kind of evened out in the end. So this is the way it's hooked up now. This now goes to a 12 volt supply. It's not to 5 volts here. So this is the RF input, a 0.1 microfarad capacitor, some protection diodes here, a 50 ohm resistor, 100 picofarad capacitor to the input here. And that yields about, 50 to 60 millivolts of input will drive this counter just absolutely fine with the cable installed directly to the circuit board. I also used one more inverter here just because it was in line. It's absolutely fine to do that. All the other inverters I didn't use are terminated either positive or negative, and I've shown this one NAND gate here as terminated to positive. You don't want to leave any gates floating or any inverters floating because that will introduce noise into the circuit. Again, you want to keep this thing as quiet as possible. I don't show the bypass capacitors or anything on the schematic because it would just really clutter this up, but there are bypass capacitors across each IC in here. And that's pretty much this digital schematic. This is the power supply schematic for this Nixie Tube frequency counter, and before I start explaining this here, this does create high voltage, and it is also plugged into the mains, so if you're following along, you're doing so at your own risk. Know the risks and precautions of working with high voltage. If you don't know that, I strongly suggest that you do not build this schematic. So this is the input transformer here. It has two primaries on it, and they're both just hooked in parallel, and this steps voltage down. So at this point here, we get rectified about 12 to 13 volts DC. If you use Schottky diodes, if you don't, you'll probably get about 11 volts or so, something like that, maybe 10 volts at this point here. So this is filtered by a 2200 microfarad at 25 volt capacitor here, and that just runs down into the ZSR 500 voltage regulator, and I get regulated 5 volts out at this point here. Now the secondary of this transformer attaches to the secondary of this transformer, and I get a step-up effect. The primaries of these transformers, again, are hooked in parallel, and this goes to a voltage doubler and out to the Nixies, and it just happened to work out better that way. You're probably saying, why didn't you just hook both of these windings in series and do it like that? Well, again, this just worked out better this way. And that's just how simple the schematic is. The reason that I'm using a separate transformer here is I get really good isolation by doing that. So this is completely isolated from the line by having this separate transformer, and I really like the way that they've wound them too. You know, the secondary and the primaries are really separated from each other. This is how the frequency counter goes together. So I take the counter board like this and put it in my hand. Of course, I know the capacitors are discharged, and there's no AC applied to this. There's no line cord on this or anything yet anyways. Take the bakelite box, put the bakelite box on top like this, turn it back upside down again, and that way the board won't fall into the box. It doesn't catch on these little steps here. So once that's in, I'm using nylon standoffs. These are little spacers and standoffs. And the reason that I'm not using metal ones is because this is getting threaded into bakelite, and if I'm going to be taking this thing apart to program it, I don't want to be threading a metal standoff into bakelite a whole bunch of times because it's going to eventually take the threads out. So this is nice and soft, and it'll preserve the threads, and they're nice and strong. They only have to be finger tight. There's no reason to torque these things down. So I just thread them in like that. On the board itself, you'll notice a little spring here, and that's to the RF ground. The screw that fastens the upper board is right in the center, and it's easily removable. It'll just come right out of the center of the spring. And the reason that's on that RF ground is because the bottom cover here has got copper on it, and that shields this whole counter. If this thing's going to be sitting on top of an old radio, usually right below the wood, inside the radio is, you know, the entire chassis, and it's open. A lot of them have glass tubes, and I just don't want to take any chances of the radio actually hearing any of this. So this is just a little bit of extra shielding to protect that from happening. So this just fits on the bottom like so. It's a really nice fit. Everything works perfectly. You can see the spring action, it's holding it up. So I know that the spring is making contact to the copper there. And the fit is really nice. You can see it's pretty much absolutely flush with the bottom of the unit. And then all I do is I take these little rubber feet here, and I can just thread them in. Of course, I'm going to be using a screwdriver to tighten these, but I'm just demonstrating this right now. And put all of the feet on, and it'll hold this whole thing together. Now, I haven't put in the line cord or anything yet, and that's what I'm going to be doing next. So the factory Numicron clock cord is in very, very nice condition, so I may just use that. And what I'll end up doing is I'll run the cord in here, and what it's going to do is going to run around here, and it'll be in a piece of that fibrous pipe that has a silicone coating on the top of it. It's that high heat stuff. It'll run around here and around this, and then back down to here again, and then I'll put one tie strap in here, and that'll be the restraint for the cord. And the coax that runs in here will do the same thing. It'll run up here and then run out as well. So this will be the restraint, and that'll hold everything nice and tight. So I don't want the cord pulling on the circuit board or anything like that, because it'll remove these pads. And of course the little pads here where the RF cable runs into are, very, very touchy. They're very small pads. I don't want to rip them off. So I'll be using, this as a cable restraint and some zap straps, and that should work out very nice, and it'll look good as well. So I'll get that all happening here, and then we'll take some measurements. As a final test for this little frequency counter, let's take a look at the RF input section with this analyzer, and we're going to do that for a whole bunch of reasons. And I'll start with my explanation over here at the counter. So this piece of coax cable here is what feeds the signal into the counter. It'll be in C connection on the end here. So in line with the center conductor of this cable is a 0.1 microfarad capacitor. That 0.1 microfarad capacitor is acting as a DC block. So if I ever, say, apply DC to this coax accidentally, it's going to protect the front end of this frequency counter. So that's in line with the coax. So at the far end of that capacitor is a 50 ohm resistor to ground. So basically, if you were to take that capacitor and short it out, it would be like putting a 50 ohm resistor right across this cable. That 50 ohm resistor is called a termination. That's a 50 ohm termination. And the reason that we need that there is to stop any signal reflections. So the whole system is 50 ohms. This is 50 ohm cable, this is a 50 ohm connector, and the little buffer board that I'm going to design in the near future is going to have 50 ohm drive capabilities. The reason that I want to keep the impedances all the same and everything at 50 ohms, again, is to stop signal reflection. This little device here is an analyzer, and it looks at that. So it analyzes a thing called standing wave ratios, or SWR. It's going to look at the impedance, and it's also going to look at a thing called reactance. And on this machine, we want that as close to 0 as possible. So when we're looking at the SWR, we want that to be as close to 1.0 to 1 as possible. And of course we want this to stay as close to 50 ohms as possible to reduce those reflections. So basically, I'll link in another video actually, just down below the Show More tab. It's on time domain. It's on a time domain reflectometer that I put together a long time in the past. And it explains all about reflected signals. So basically, just to simplify this right here, right now, you can kind of look at this RF signal as radar. So what happens is this device is sending RF down the coax, and it's going into this little frequency counter here. What's happening is there's a termination in here at 50 ohms, so the signal doesn't come back up the coax and go back to the machine here. If I was to remove that 50 ohm resistor here, there would be no termination inside this, and I would get signal reflection. So the signal that's being sent down the coax would hit the end of the coax and rebound back and come back up to here again. Kind of like taking a rubber ball, a hard rubber ball, and throwing it at a hard wall. When you put the termination at the end of the coax, it's like taking that hard wall and putting a mattress there. So basically there's something at the end to absorb the energy. That's how you can look at this. So I explain more about this in that time domain reflectometry video. So you kind of look at this kind of like radar or something like that. So basically we want to keep this thing at 50 ohms through the entire frequency range, and we also want the lowest SWR that we can get through that entire frequency range, and that would be up to about 41 megahertz is where this thing topped out, right? So when I designed this thing, on the bottom side of the board is that little RF preamplifier. And the reason that I put it on the bottom of the board is because RF input sections to frequency counters and analyzers like this are very susceptible to damage just from even just the most minor overlook, basically. So many people destroy these machines just by putting a piece of coax into it that's attached to an antenna outside their house. If you have an open wire antenna on the outside of your house, the coax will act like a capacitor and it will charge up, and you'll get a high voltage charge on that coax. You plug it into the analyzer and the front end of the analyzer is gone. So it's a very sensitive section in this, and the RF front end in this thing is also very sensitive, and that's why there's protection. There's also some back-to-back diodes in there and stuff after the blocking capacitor to suppress any kind of spikes or anything like that. But again, I built that RF section on the bottom half of the board. Just in case something does happen, all I have to do is turn it upside down, take out 4 screws, and that little RF section is right there, and I can just replace the components. In fact, the case even holds the circuit board for me. So that's just good design practice. Keep anything that's very susceptible to damage in a place where it's very easy to service. So anyways, back to looking at the actual signal that's going to be sent in here and see how well this thing responds. So what I'll do is I'll turn on the analyzer here. That's just it going through its cycle here. All right, so what I'll do now is I'll hook up the coax running directly into the counter here. In fact, this thing actually has enough drive power to make the counter read throughout its entire range. So here we go, we're at 2 megahertz right now. Our SWR is 1.0 to 1, so we want it as low as possible. 1.0 to 1 is great. The impedance, 47 ohms, absolutely great, X equals 0. So doing wonderful down here. So just like everything at Mr. Carlson's lab, this is modified too. And I've modified this just to do this particular kind of work. And anybody that owns one of these things will recognize the difference right now. Right now we're at 991 kilohertz. So we're right in the middle of the broadcast band, really. This here is 1.0 to 1 SWR. Impedance 46 ohms, X equals 1, doing great. Now we're at 600 kilohertz or 600 AM. 1.1 to 1, absolutely fine. 45 ohms, X equals 4. No problems whatsoever. So this is back to normal operation now. 4.6 megahertz, everything's great. 11.57 megahertz, great. As you can see, the SWR is basically staying flat. 29.9, no problems, 54 ohms. Fluctuating a little bit above and below, absolutely fine. X equals 0 here. 65 megahertz. Now we're beyond where this frequency counter will even operate. It caps out at 41 megahertz, so this is really just icing on the cake. Look at that, still 1.1 to 1, 45 ohms, X equals 2, not a big deal. So just for fun, let's go right into VHF, right up to the top. Look at that, 117 megahertz, 1.1 to 1, 45 ohms, X equals 7. Couldn't ask for anything better. So just to give you an example, if I was to take that little termination resistor out of there, this would go way high. So for example, if this was say 2 to 1 right now instead of 1 to 1, if it was 2 to 1, I would be looking for problems in coax because I would have some pretty big issues at that point. If this was 3 to 1 at this point, I would be completely redesigning something in here. There'd be something really wrong. Maybe the coax would have a pinch in it, or it's shorted, or it would be the wrong impedance or something like that. So that's basically what we're looking at. 3 to 1 would be the absolute maximum. And believe me, this meter is not giving at all. So it's a very accurate device and it's working very well. So all in all, this thing is working great, and it's goes well beyond where it needs to go. It's basically just supposed to cap out at 40 megahertz here, 41 we can bring it to here, and you can see everything is absolutely fine. So whenever you're designing any kind of RF system, that's absolutely important to do. You need to make sure that your coax is terminated, because put it this way, if I installed a buffer inside of a radio and this had a lot of reflected, so basically this thing had high SWR or something like that, that buffer would need to fight that. So the buffer would need to actually put out more power. So if you're a ham radio operator or a broadcast engineer, you definitely know that SWR is your enemy. I spent some time and cleaned up the bakelite case of this old Numicron clock now turned into a frequency counter. My other half took some pictures of the frequency counter, and this happens to be my very favorite picture. Just look at the detail of that bakelite. They did a really nice job when they put that case together. Thanks for stopping by the lab today. Hope you enjoyed this series on building a Nixie Tube frequency counter. If you did, you can let me know by giving me a big thumbs up and hang around. There'll be more videos just like this in the very near future. If you're interested in the rest of the series that led up to this video, just below this video is a Show More tab. Just click on that Show More tab and I'll have all the other videos of this series linked in there. All right, take care. Bye for now.